On this slide, you can see a full set of main functions that describe any distribution, which is probability density function, a cumulative distribution function, and inverse cumulative distribution function. And then you can see that average is equal to 0 and standard deviation equal to 1 in both these cases. So it means that this is the standardized distribution. So this is distribution of z-scores. And what you can see, first of all, you can see this very clear bell shape. And you can also see this S shape for CDF function, which we also discussed a little bit when we just introduced the normal distribution. You remember this example with height of adult female persons in the United States. This height value is the percentage plot that looks like a S-shaped plot. And that's exactly why, because it's normally distributed values. Okay. If you think about distribution of real values, then it looks the same. It's just the shape is a little bit different because now you have the values here instead of just z-score. So for example, you can see that here I have average is 170, standard deviation is 10 in all these cases, and this is how it looks like. Like in uniform distribution, R has these functions for normal distribution. So first of all, it's this PDF, CDF, and ICDF function. You remember in uniform distribution, it was a D function because it's density, the unif we call it, the unif. Then we have P function that provides probability, P unif. And then we had Q function that provides the quantiles, it's the value for given probability, unif. And then finally, we also used in one of the examples R function, which takes a random sample from the population, right? So you remember that this D, P, Q, R, it's the name of the functions, density, probability, quantile, and random. And unif, it's the name of the distribution. So if you change unif to any other names of the distribution, you will get these 4 functions for any distribution which is implemented in R. In our case, we have normal distribution, and a normal distribution name in R is just a short norm, and that's why you have D norm function, P norm function, Q norm function, and R norm function. Any function has, of course, the argument. For example, for D function and for P function, it's your value. Then for Q function, for ICDF function, it's a probability. And then for taking a random sample, you need to provide a sample size. Then you can also provide these 2 parameters, the average and standard deviation of your population. But if you don't do that, then R will think by default that you want to get a value for normal distribution, for standardized normal distribution, for z-score. So it will assume that the average is 0 and standard deviation is 1. So if you indeed need, for example, density, probability, or quantile for standardized normal distribution, then you simply skip these parameters. But if you want to get this for particular values, for particular population, then you need to provide parameters of this population. Okay. Now let's use this knowledge and let's, for example, prove, of course it's not mathematical proof, it will be more experimental proof, this rule. You remember that we have 68.3% of all values in normal distribution population, normally distributed population, within 1 sigma from mu, around mu. 95.5% of all values lie within 2 sigma around mu, and then 99.7 lies within 3 sigma. So let's try to prove this. Well, first of all, let's take the first rule. So this one, 68.3%. And this is how we can show this rule, at least for one of the tails, for minus 1 sigma, in using PDF and CDF function. This is not P, this is CDF function, okay? So you can see this is exactly average plus minus 1 sigma. So this is average minus 1 sigma, right? And this area gives us the probability to get a value smaller than this one. And then if you can see, this is the value, right? So it's 0.587. We can also get this value in R. You remember that the function that gives us probability for given value, it's CDF function or P function. So I simply say P norm minus 1. It means Z equal to minus 1. So I assume that mu is equal to 0 and sigma is equal to 1, right? So 1 standard deviation below, and that's exactly the value that I have here, just round it, okay? So if you take 1 standard deviation above mu, exactly here, right? So this is the probability to get a value smaller than this one, right? So you can see that this is 1 standard deviation above mu, and here we have also 1 standard deviation above mu. Again, we can compute it in R by running P norm from 1, so Z equal to 1, meaning one standard deviation above mean, and that's the probability. What we look for, it's the value in between, so this area. We need to find this area, and we know how to find it. It's this probability minus this probability, right? And if you do that, you simply write p norm for one standard deviation above mean minus p norm for one standard deviation below mean. So this gives you this area, the big one. This gives you the small area, this one. And that's exactly the area in between, which is, you can see 6826895. But if you round it to 3 decimal, it will be 0.683. So, or 68.3%, exactly what we actually have here. Okay. So this is kind of empirical or experimental proof of this rule. Now, let me show you an example. How many adult women in the United States are taller than 180 centimeters? How we can answer this question? First of all, we Google, and we found out that actually the average for adult women, the average is 64.3 inches, and the standard deviation is 2.58 inches. So I know the parameters of my population, and then I simply use this to compute these two values in centimeters. It's just easier for me. And now I know the population parameters, so I can use the normal distribution CDF and ICDF function to find the answer, right? So in this case, I need to find how many, so it means I need to find a percentage. So in this case, of course, because I use theoretical function, I'll find a probability that then I can think about the future, the measurements in future, and then I can think about percentage as well. So in this case, because I need probability for given value, I should use CDF function. So I say CDF function for 180 centimeters for these given parameters. So this is CDF function for these given parameters, and then you can see that this is the probability. Or if you think about PDF function, it means that I need to find an area under this PDF curve on the left, area on the left, because in CDF function, I always calculate area on the left, although in fact I need area on the right, but let me keep this so far. So area on the left gives me a probability to find a person, a female person, whose height is below 180. So it's not taller, but smaller than 180. Nevertheless, we can compute it by using CDF function. In R, we simply write P norm. You remember probability function, CDF function. This is the value we are looking for, and this is the parameters of my distribution. So now I use parameters, so it's not standardized distribution, and this is the probability, right? But because I need to find person who is taller, I need this tail. But I cannot compute right tail in CDF. However, I know that the total area is equal to 1. So if I want to find this area, I simply need to subtract 1, the probability that I calculated before from 1. And that gives me the probability. Now I know that if it's a probability of 0.115, if you think about the percentage, if you think about the whole population, so it gives you 1.15% of this population. Okay. Now I can also Google and see, for example, that you have the population of, in the United States, if you take all adults 18 years or over, you can see it's approximately 108 million. And I can take 1.15% of this value, and that gives me exactly the answer. So I can expect that approximately 1.2 millions of adult females in the United States are taller than 180 centimeters. So you just need two parameters. You don't need the values. Of course, you need the values to get the parameters, but someone actually already did this for us. So we already have these parameters based on probably a very large sample size, not the whole population perhaps. But nevertheless, we assume that these parameters are represent the population very well, and we can use these parameters to do the computation. Okay, so this is again overview of these functions in R, and now let's prove another thing. To remember, I also told you that 95% of all values lie around mu within 196 sigma. So they cannot go beyond this plus minus 196 sigma in 95%. So let's try to think how we can prove it. If you think about a standardized normal distribution, it means that you need to find two values, Z1 and Z2. So in between, if you find area between these two values under this distribution curve, you will get 0.95. How to do that? Well, now we have the opposite, the other task, right? So we know the probability but we don't know the values. So it's a job for ICDF function, for inverse distribution function, cumulative distribution function. But first of all, we need to recall the probabilities on the tails. So if it's 0.95 here, it means that it's 1 minus 0.95, which is 0.05 outside. But because outside means on both tails and distribution is symmetric, we need to take a half of this. So you get 0.025 here and 0.025 here, right? Now we know, for example, for Z1, this area that we are looking for, it should be 0.025. So we need to find kind of 2.5th percentile for our distribution. But we know it's a job for Q function. Q function gives you quantiles, so you simply provide probability. In this case, because it's standardized distribution, I don't need to provide mu and sigma. And that gives me the value, which exactly, not exactly, of course, but if you round it to 2 decimals, it's minus 196. Okay. Now, how to find the second value? Well, apparently, for the second value, you need to find all area on the left. You remember that this is 95, this is 2.5. So together, how much you have on the left of Z2? It's 95 plus 2.5, it's 0.975, right? So the probability for Z2, it's 0.975. So we need to find 97.5th percentile, right? So exactly we know what to do. We simply write Q norm with this value and we got plus 196 if you round it to 2 decimals. So that will be plus 196, or just we can say that indeed, if we talk about theoretical normal distribution, 95% of the values around mu are located between minus 196 and plus 196 standard deviations. Measure it from the mu. Now another example how we can use ICDF function. I came back to this population of all adult females in the United States. We know the parameters of this population. Now the question is, let's find a range of 50% of most common values, so 50% in the middle. Okay, so this is how it looks like. So if this is distribution of all height, this is the parameters of distribution, then we need to find two values, right? So two values. So if we find the area between these two values, we have 0.5. So we're actually looking for IQR, right? So we're looking for the quartiles. Well, we know that if we want to find the left boundary of this interval, we need to find a 25th percentile, right? We need to find a value. So 25% of other values from this population are smaller than this one, okay? Again, it's a job for ICDF function or Q function. In this case, I can either just write Q norm 0.25. It gives me how many standard deviations I need to go. So it means that I need to compute this manually. So I need to say 165 plus Q norm times 6.6. And this gives me the minus, and that gives me the value, right? Or I can run this function with parameters, right? So instead of using standardized normal distribution, I use normal distribution for this particular population with these given parameters. So you can see I provide parameters, and you can see the value is identical. The value is identical, okay? Remember, Q norm, if you write it like this without parameters, that gives you this score. So here, in this case, I simply write like x equal to mu plus z sigma. So you can see this is mu, this is z score, and this is sigma, right? But if I write it like this, I provide parameters of this population, it's done automatically. So I don't need to do manual calculations. So this 160.55, it's the left boundary. It's Q1. Now for Q3, I need to find 75th percentile. So I just do the same, but I set probability to 0.75. Again, I can use it for standardized normal distribution and then calculate the real value, the real quantile manually, right? Or I can simply provide these two parameters to Q norm function, and you can see the result is identical. The result is identical. Now I can answer the question. So if you take 50% of the most common height values for adult females in the United States, this bounded by approximately 160 and 170 centimeters. So 50% of most common values lie within 160 and 170 centimeters. So it means that in this case, the IQR is approximately 10. In this case, it's actually a little bit smaller. You can see if you take a difference, it's exactly 9 centimeters. So that's the theoretical IQR. So now you know how to use ICDF and CDF functions on practice for for solving some practical tasks. To kind of strengthen your understanding, I recommend you to watch the next video, which will be about Grasta app. I have a dedicated app for PDF and CDF and ICDF functions for two distributions, for normal distribution and for uniform distribution. So you can switch between these two distributions and play a little bit. And then just watch next video about this Grasta app and then play a little bit with this application. I highly recommend you to do that. And then come back and we will continue discussing a normal distribution.